In this video, I'll draw equipotential surfaces or equipotential lines for a +8 nanocoulomb point charge. I'll draw them for 1 volt, 2 volts, and 4 volts. I've used the simulation flashphysics.org, which actually doesn't work anymore because Flash Player no longer exists. But I used an online simulation to create these field lines. This simulation doesn't create arrows, it only creates the lines themselves. So for these electric field lines, we know that since this is a +8 charge, they point outward. So really, the field lines look like this. These aren't equipotentials, these are the electric field lines. To draw an equipotential, we need to find all the locations where the potential is whatever value we're looking for. This mathematical model gives the electric potential or voltage caused by a point charge of charge Q. This one, remember, is for a uniform electric field. This one does not work with point charges, so we cannot use that one. We're going to use this one. So the V's, these are the potentials we're going to be looking at. We're going to use 1, 2, and 4 volts for that. So the V's are known. K is a constant. Q is +8 nanocoulombs. So we can rearrange this to solve for R. So R equals KQ over V. Now all I have to do is put in K, put in Q, and then put in the different V's, and I'll find the different R's. So I've made a table here of what happens when I put in a V of 1 volt, 2 volts, or 3 volts. I get that R is 72, 36, or 18 meters. So if I call this distance 72, I draw a circle with a radius 72 meters centered on the charge, and then I label it that this is 1 volt. 36 meters is half this distance, so that's where 2 volts is. And then 18 meters is half of 36, so this is where 4 volts is. You can see that these equipotential lines are getting closer and closer together as I approach the charge. And in fact, if I had put the 3 volt line in, it would be even more pronounced. So the electric field lines are far spread out here, and the equipotential lines are also spread out in the same area. As the field lines get closer together, so do these equipotential lines. Also, you should note that in every place, if I was good at drawing circles, the equipotential line crosses the field line at 90 degrees. That's always true for any charge configuration. So whenever the electric field lines are getting closer together, so are the equipotential lines, and the equipotentials are always perpendicular to the field lines.